All right. And thanks for inviting me. I'm very happy to be giving this seminar to all of you. So, oops. I hope everybody can see my screen and yeah, great. So here's a quick agenda for the next hour or so. Essentially, what I will be talking about it will be mostly based on a recent review paper that we published in statistical science with the same title, Modern Bayesian Experimental Design. My talk will be split roughly into three parts. The first one will cover sort of variational Bayesian experimental design. The second one, I will introduce what we call a policy-based approach to Bayesian experimental design in the deep adaptive design framework. In the third part, I will briefly touch upon a few papers that we published on the topic of sort of extending Bayesian experimental design beyond parameter learning to what we call goal-oriented BED. And I will conclude with some sort of limitations of current approaches and sort of the things that I'm currently working on and future directions. I do want to say, please feel free to interrupt me if you have any questions. Given that it's also online, it can be a little bit boring and people get Zoom fatigued. So let's try to make it at least a little bit interactive. And yeah, any questions, please feel free to interrupt directly. I probably won't see you if you raise your hand via Zoom. So yeah. Okay. So just as a brief sort of motivation, I guess this audience doesn't really need it. But what is experimental design and why do we care about it? Many different questions from science and engineering basically constitute the same underlying fundamental problem, namely, how do we design experiments to collect data that will help us learn about some underlying process that we're interested in. Some examples include things like designing online surveys. The most classical example, obviously, things like running experiments in a lab. So, think about drug discovery, what compounds go well together, how can we speed up the drug discovery pipeline, to also things like actually improving machine learning models. So active learning can be thought of as a special case of Bayesian experimental design as well. And throughout this presentation, I will sort of stick to this quite simple problem, but hopefully gives the necessary intuitions and establishes sort of the necessary notation that will be helpful as we go through. So as I said, it's a simple survey style problem that tries to determine the individual's subjective time value of money preferences. So the way that this is done in contexts of psychology and behavioral economics is by asking various participants a series of questions of the form, do you prefer some money now? Let's say, do you prefer £100, £150 now or £100 in 1 year? And there's many, many different questions that we may choose to ask. And clearly, sort of the first one is an example of a very bad question that we can ask because everybody will prefer more money now as opposed to less money in the future. Whereas the second question, do you prefer £50 now or £100 in 1 year? You may get different answers depending on who you were to ask. So if you ask a poor graduate student, so I made these slides when I was still a graduate student. I guess I'm no longer a graduate student, so I should update my example a little bit. But a graduate student may prefer the cash now, whereas a professor may prefer to wait to get a higher reward. So we want to find a way of formalizing why the second experiment is better than the first one in some form of a quantitative manner. And to do this, we are going to take an information-theoretic approach. So the design that we choose is going to be the one so that when we run an experiment with that design, the data that we end up collecting will be as informative as possible about the underlying quantity of interest, right? So I'm going to denote the, can you see my cursor?
Yep.
Yeah, great. So I'm going to denote the underlying quantity of interest by theta. Our designs will be denoted by xi, and the data that we collect or the outcome of the experiment will be denoted by y. And in Bayesian experimental design, we formalize the relationship between these three quantities in a Bayesian way through a probabilistic generative model, on sort of a probabilistic joint model, P of y comma theta, given our design. We normally factorize it as a prior on our parameters of interest, P of theta, times an observation likelihood, or the forward model. And again, in a standard way, the product of the two gives us something that is proportional to the posterior on the unknown parameter of interest, P of theta, given our outcome of the experiment and the design of the experiment. So going back to our example, to kind of put things to sort of this survey example that we started with, our design will constitute the tuple, the reward now, and the delay that we're going to offer to the participant. The outcome of our experiment is the participant can either reject or accept the delay. And theta is an underlying model parameter that sort of governs how people choose what people's preferences are, essentially. This is the precise form of the model that we work with. It's not super important, but it's available there in closed form. Now, what do we mean by saying a maximally informative design about the underlying quantity of interest? A very natural way of assessing the information content of an experiment is the what we call the information gain, which is defined as the entropy of our prior minus the entropy of our posterior. So we can compute sort of the uncertainty about the parameters of interest under our prior. And once we perform an experiment and observe the outcome, compute a posterior, we can compute the entropy or uncertainty of that posterior. And the difference between the two sort of constitutes our information content of an experiment xi. Then the optimal design will be the one that maximizes the expected information gain, right? In order to actually get a quantity that can be useful for ranking experiments before we observe the outcome y, we simply take an expectation over the all possible outcomes that we can observe under the experiment xi. So this is pretty standard. This has been done back in the day, so 70 years ago, by Lindley. And since then, we have sort of figured out that there is many or a few different formulations of the EIG. Namely, we can write the expected information gain as the mutual information between parameters and outcomes. We can also view the EIG as an expected utility with a special utility function, namely the KL divergence between the posterior and the prior. And also we can draw a connection with the active learning literature and basically see that the EIG is exactly equal to what is called the Bayesian active learning by disagreement, or BOLD score. Now, there is a few different formulations that we can use, but all of them share sort of the same underlying problem, which makes it rather difficult to work with in practice. In this slide, I'm sort of summarizing the main challenges, if you wish, of what I'm going to call vanilla Bayesian experimental design. The first one is that our objective, the expected information gain, is really quite computationally costly to work with. It is a quantity that is referred to as doubly intractable, right? It is an expectation, and inside the expectation, we have intractable quantities that need to be approximated numerically. The second one is that once we start repeating experiments in an adaptive way, so if we were to do adaptive experimental design, because of this, because of the need to perform repeated computations of both the posterior and the EIG estimation and optimization, this makes it really rather slow to run adaptive experiments, and basically we can't really deploy these in real-time experiments. Number three, the way that I describe this setup is that we are optimizing or maximizing information gain, expected information gain about all of the parameters in our model. And it might be the case that, not all of the parameters are actually needed for what will be useful for the downstream decision making. Right. And we'll see that a few examples of that in a second. And finally, as any model-based framework, it is very susceptible to model misspecification. And Bayesian experimental design is especially sensitive to misspecified models due to the fact that it sort of relies on that model twice. Number one, to gather the data, and number two, to then fit that model. And in this presentation, I will be touching upon the first three sort of challenges. So computational intractability, I'll show how we can improve scalability and allow for real-time deployments. I'll touch upon some sort of goal-oriented formulations that take into account the downstream task. And model misspecification is something that myself and our group in Oxford is currently actively working on, and are looking to work on more in the future. So I think this is a natural point to see if there are any questions, or should I continue? No questions.
Oh, no questions, I think.
Great. So I'll give a brief overview of variational Bayesian experimental design. And let me just recap what we had. So we have the EIG, the expected information gain, which we said is doubly intractable. Regardless of the KL gymnastics that you may choose to do, we end up with an expectation, right, that we will be estimating numerically of a log density ratio, either between the posterior to the prior or the likelihood to the marginal. And in each of these cases, you will have something that is typically intractable. Now, the key idea here will be to use optimization to approximate some of these unknown densities. And the key requirement for this will be basically only being able to sample from the joint model in kind of the most general case. Here is a brief overview of how things are typically done. So this is the nested Monte Carlo estimator, or double loop Monte Carlo estimator, as is also known in the literature. So we have our expectation of, in this case, I have written the likelihood divided by the marginal formulation. And the issue that we have is that this quantity is intractable, and it's also different for each sample of yn that we have for the outer expectation. And here is the double loop sort of Monte Carlo. For each sample y, we resample parameters from our prior to estimate with simple Monte Carlo the unknown marginal. Now, the convergence of this, again, because it is a nested estimator, is actually much slower than traditional Monte Carlo methods. Due to the log, due to this nonlinear function that we have, this estimator is also biased, but in the limit, as L tends to infinity, we do get an asymptotically consistent estimator. Now, what we can do, a simple thing that we can do is, rather than estimating this quantity P of yn given the design from scratch each time, is that we can treat this problem as a form of stochastic regression and actually learn a functional approximation to P of y using, some function Q that I'm going to parameterize with some parameters psi. And again, this will be available in closed form. So rather than sampling every time, we can just plug in our y and obtain an approximation, very, very, very quickly. Now, the cool thing is, if Q happens to be a valid normalized density, we end up having a variational upper bound on the mutual information or on the EIG, which is also tight if and only if the parameterized approximator is actually equal to the marginal distribution. Again, because we are evaluating a function rather than sampling, we do recover the convergence rate of the standard Monte Carlo estimator, but this variational form will remain biased unless we're able to learn the true marginal.
So this means that the error is 1 always, even if t gets large? Correct.
So even if t gets large, if Q is not flexible enough to learn the true marginal, we will get something that is not consistent even in the limit as t grows.
Thank you.
Having said that, by choosing, so as I mentioned, there is a bunch of densities that we don't know, and we may choose to approximate. In this case, I chose to approximate the marginal, but if we were to approximate the posterior, instead, we are going to get a respective a respective lower bound on the mutual information. So this one gives us a variational upper bound. Approximating the posterior will give us a variational lower bound. So the cool thing is, although our estimators are biased, we may get a sense of how biased these are by computing the respective variational upper or lower bound. So basically, we can sandwich the true expected information gain in a relatively efficient way. It will require some training of these parameterized densities, but once these are trained, we can very quickly estimate the EIG, both the upper and both its upper and its lower bound. Okay, so now we can estimate it relatively quickly, but we still need to optimize it over all possible designs.
Can I have a question?
Yes, please.
But here, do you train this approximation on the fly, or do you do it a priori?
We do it a priori.
Okay, thank you.
Yeah. Now, what I just described involves, and this is actually a very good question. So what I just described involves training a variational upper and lower bound for each psi separately. And clearly, this becomes very quickly quite computationally expensive as well. So what we can do is actually formulate a unified objective that will allow us to train to train our variational bound, which is parameterized by psi, and optimal design denoted by xi simultaneously, right? So you can think of it as a single stochastic gradient scheme, optimizing with respect to psi tightens the bound, and optimizing with respect to xi kind of maximizes it. This was done again quite a few years ago by our group in Oxford and also a group in Edinburgh. And kind of the summary of this line of work is that we can quickly and efficiently estimate and maximize our expected information gains with stochastic gradients. Now, this hasn't really solved the adaptive experimentation pipeline, however. As I just said, we can very quickly maximize the EIG, but the Bayesian experimental design pipeline then involves performing a posterior update once we obtain our outcome and re-optimizing a new expected information gain using our posterior as the new prior. Okay, and clearly, both of these steps, again, will require quite a substantial computational cost, which means that, it is unreasonable to expect that we can run these things in real time, as, for example, is the case in this sort of time value for money subjective kind of psychology experiment. So how can we approach this? Again, it was a couple of years ago, we sort of came up with this a slightly different, I guess, approach to designing optimal experiments that we sort of termed policy-based Bayesian experimental design. And this is sort of the high-level picture. We are going to start with our model, right? So we have our joint model, prior times likelihood, and we're going to perform an extensive offline pre-training that will produce a policy which can then be deployed during the live experiment for quick and adaptive design decisions. Now, what is this policy? It is just a function, right, that takes in past data, so the previous designs and experiments as an input. We're going to pass this data through our policy, and it will immediately produce the next design for the next experiment iteration. Now, I want to highlight that the traditional, so the vanilla Bayesian experimental design that I just described, this two-stage expensive pipeline that constitutes of two steps. Number one, do a posterior estimation. Number two, perform EIG maximization is a special case of this, right? We have an implicit policy that consists of those two steps, which is slow. So what we're going to do instead is come up with an explicit policy that we're going to parameterize with something powerful like neural network that will take in past data as an input and produce the next design immediately with a single forward pass through that neural network. Now, how are we going to train this? What we want out of our policy network, of our parameterized neural network, is to amortize or emulate the slow adaptive design. In other words, we want to maximize the expected information, the expected sum of individual information gains. So we have at each experiment iteration, we are gaining a little bit of information gain. We're summing that, and this is sort of our objective that we sort of want to maximize, that we want our policy to maximize.
Question.
Yes.
Why is that the objective and not just the final information gain between what you knew at the beginning and what you know at the end? Essentially, the prior at essentially zero and the posterior at essentially step T capital?
Yes, so great question, and the answer is they're exactly equal, which is basically what we use. Excuse me?
This is slide says essentially, right?
This is, sorry, I can't.
This is what this slide slide is essentially, right?
Yes, exactly. Okay. Yeah.
But I mean, I think the argument is inverted, right? I mean, what you want is really the right, and then you rewrite it as the left for just convenience.
Yeah, I think our thinking process at the beginning was the other way around. We were sort of thinking of ways to actually computationally compute in a computation efficient way compute this because of how the traditional adaptive design is performed, and then it is pretty it is kind of obvious. It's just mutual information chain rule to show that this is exactly equal. So the information from the prior to the posterior, or the expected reduction in the entropy from the prior to the posterior, because of how Bayesian updating works, is exactly the same if we were updating our posterior sequentially. It's just like the mindset that we had at the beginning was we should be doing the sequential updating rather than kind of the total update from t equals 1 to t equals capital T.
Thank you.
I'm sorry, I interrupted. I also have a question. I think about this every
Please.
slide. You did excellent introduction, but what if I do not have probability density function in high dimension? It may not exist. So do you have alternative formulation, maybe for probability characteristic function, or maybe if all moments are available, or maybe polynomial chaos? Maybe
Yes.
polynomial chaos expansion.
Yes, we do. We will see in a couple of slides. We will be able to train policies both with likelihood-based models and models where we don't have the likelihood. So if we're only just able to sample from our model.
Excellent. Second question. This theory, information gain, and they are like 100 years old. Fisher was born 1890. It would be maybe nice if you can highlight what is new, what is recent in this area. Because once I was also doing this topic a little bit, and for 100 years, matrices were 2 by 2, 3 by 3. Now matrices are 1 million times 1 million, or we have multidimensional, we have tensors. Is it something new here in Bayesian information gain theory?
So the expected information gain, it dates back to Shannon and Lindley, not Fisher. So that's a little bit later, but still, it's not 200, it's 70 years old. But yeah. The information theory, there isn't anything new on the information theory aspect, where sort of the innovations and advances are in how we can use modern techniques from sort of optimization, variational inference, and sticking neural networks pretty much everywhere to solve exactly what you mean, right? To solve very high dimensional problems, very complex problems, and different data modalities and so on.
Thank you.
Thanks for your questions. Okay, so again, so we have established that the expected information gain from the original prior to the end posterior is exactly the same as doing the incremental update. And the nice thing about the total expected information gain formulation is that we have a single expression, which is still intractable, but it will be more amenable to being optimized using stochastic gradient schemes. How we can do that? Well, basically, we can approximate the outer expectation by sampling first from our prior and then use the current policy. It doesn't have to be the optimal policy. We will be training the policy as training is performed. So we're going to use the current policy to create a design sample the outcome, and then for the inside of the expectation, again, we can use basically the variational EAG estimators that we previously discussed. And the simplest thing that we can do is optimize, assuming, again, so here I'm going to first assume that our likelihood is available in closed form. And it is only the marginal distribution that is intractable. What we are doing here is it's a version of the nested Monte Carlo estimator where we are adding the primary samples, so the sample from the numerator into the denominator, which gives us a lower bound on the total expected information gain. Now, this is a quantity that we can plug into our favorite stochastic gradient optimizer and train it end to end using just samples from our model and evaluations of our likelihood. We just had a question about what if we don't have a likelihood? Well, what we do is introduce another small model. So we're taking inspiration from some of the advancements in the representation learning literature. So we have the info-NCE lower bound on the mutual information from Banden or 2018, and the NWJ bound on the KL divergence from 2010, which are readily applicable to our case. So what does this involve? It involves training, as I said, a small model, which in the literature is called the critic network. It is a function that, again, I'm parameterizing with the same parameters as our, oh no, it's not the same parameters. Sorry. Our policy is parameterized by phi, and our critic, this sort of extra model, is parameterized by psi. It takes as an input our history, so our design and outcome pairs, the entire size t history of it, and a parameter, and produces a number. And essentially, when we train it, it learns to approximate this unknown density ratio, whichever way, either the likelihood to the marginal or the posterior to the prior. And here is a kind of a review slide. I have included the equations for the estimators that I just introduced, the NWJ and the info-NCE. I don't think there is particular value in going through them necessarily. The only thing that I want to highlight is that there are some bias variance trade-offs that may lead you to choose one or the other. In case you are in a problem where densities are not available, you can again pick one or the other, and we show that things work. So yeah. So here is some numerical examples actually. So going back to our adaptive online survey, we have a two-dimensional design, simple. We have a binary outcome, and we have a closed form likelihood. And here we have trained a deep adaptive design network. So this is our policy. And I'm running a couple of iterations from a hypothetical human participant, right? So starting with 49 versus 100 in 3 months, to which the human participant prefers the money now, then the network adapts and sort of reduces the time delay, and then reduces it again until the human participant actually prefers the delayed reward, and then we can continue, right? So as the survey progresses, it sort of adapts to the very, to the peculiarities of that human participant exactly. And these are some results for this experiment. So we are performing 20 questions, and here I am reporting a lower and an upper bound on the EIG, on the total expected information gain. Again, remember we discussed the lower and the upper bound in the previous section. And here we're actually demonstrating that the bounds are quite tight. The first benchmark that we use is a model-specific. So this is a heuristic designed by some psychologists, Fry, in this Fry et al. Paper. And you can think about it as some form of a tree. So, you start with the first question, yes or no. And if the participant answers yes, then there is like a bunch of other yes or no questions that are continued with the exact numbers being fixed a priori. The second approach is a traditional Monte Carlo based one, where after each experiment iteration, there is some form of an efficient population Monte Carlo estimator being deployed for the posterior estimation. And again, because we are running Monte Carlo and re-optimizing the EIG after each experiment iteration, the deployment time of this approach is much higher than sort of the heuristic one, which is just a lookup table, and much slower than our deep adaptive design approach as well. Our deep adaptive design approach also outperforms the traditional one by quite a lot, given that mutual information is in sort of log scale. And we found this quite surprising. So when we were doing this type of work, we were expecting that once we start amortizing anything, we will be losing performance, not gaining performance. And so that result in itself was rather, unexpected. And sort of we came up with two possible reasons why we might be outperforming the traditional expensive approach. Number one, it is a bit hand-wavy, so I haven't had a chance to actually sit down and look into like all the details, but I think it is actually beneficial to try and avoid the Bayesian inference at each experiment iteration, because we sort of limit the amount of errors that can propagate through sort of this sequence of experiments. It might be the case that it is easier to learn to map past data directly to next designs, as opposed to going via an intermediary posterior and then re-optimization. And we'll see in a second, actually, a very good example. Think about it. If your posteriors are very wrong, your subsequent EIG will be optimized with respect to something that is, might be quite far from the ground truth. And so you end up in a kind of in a subspace of your designs that is actually can be quite far from the optimal. And the second reason for the outperformance, specifically in this case, is the fact that we are performing non-myopic design. So the traditional Bayesian experimental design that I described earlier is one step greedy. Again, it can be extended to kind of multiple steps look ahead. This one, again, the traditional approach of Vincent and Rainford is only looking one step ahead. Because we are sort of planning the entire sequence of P experiments from the very start, we're actually seeing an improved performance because of this non-myopic aspect. And I mean, this is just a simple example of myopic versus non-myopic. Imagine we have the task of breaking a stick in 3 equal parts. If you were doing a myopic optimization of this, you would first break it into two and then break one of the halves into other two. And obviously this is not the solution. If you were planning ahead, you can, choose the 2 points a priori and then sort of break the stick into three exact sub-sticks. Here is another example of an experiment. So this is a simple example where we're trying to locate kind of two hidden sources. And this is the learned policy. Basically, it sort of starts somewhere where the prior is the highest, which is at 0, 0. And then it sort of learns to explore the space and sort of refine its knowledge when it detects a signal and then sort of continue. For this specific example, we are outperforming, again, a traditional variational approach by quite a substantial margin. And we are performing much, much quicker compared to, so this is definitely not an optimized traditional variational BED for this model. This can be improved by quite a lot. And in this case, we have actually selected a pretty poor variational posterior family for the posterior approximation, which is basically the reason why it has underperformed so much. Since then, I have rerun this experiment with like a better variational posteriors, and the gap is much smaller, but there is still a gap between the traditional approach and the amortized deep adaptive design. Okay, I will just pause for a second and see if there's any questions at this stage. No.
Seems
Okay,
not.
great. In the third section, I just wanted to mention briefly, and I am aware of the time, so I will quickly go through a few works in the space of sort of going beyond parameter estimation. And the first one is a paper that looks at contextual optimization, but basically the goal, you can think about selecting optimal actions for your customers, such as you can give them some discounts or you can send them some emails with sort of promotions and things in a sort of context-dependent manner. So, for example, taking into account things like the age, income, and so on of your users, with the goal of maximizing some form of a reward, such as revenue. So what the goal of this specific work was to maximize some form of reward by choosing optimal actions for a set of customers that I'm denoting by capital C star. What we have as an experimental budget is another set of customers that I'm denoting by just C that will be used to, make sure that once we deploy our policy at this other set of customers, we will be maximizing the reward for this other set of customers. Okay, and here is an overview of the setup. So the experimental contexts, these are our C's, are the orange dots here. Our test context, our C star, is the gray line here. And what we're interested in is choosing the treatment. So treatment 1, the green one, or treatment 2, the purple one, so that we learn as much as possible about the true but unknown maximum value at this test context, right? So the true unknown value is this red cross denoted by M star here. And what we want to do is pick the treatments to apply to the experimental context so that we learn as much as possible about this. Okay. And again, here our quantities of interest are not the parameters of the functions, right? These are not the parameters of what explains the entire curve. It is specifically the maximum that is achieved in each of the test contexts. And this is a stylized example. We have quite a few examples in that paper actually, but for making it clear what we're actually doing here, I think this is the best one. We call our method COBET, so contextual optimization by a Bayesian experimental design. And here on the left and on the right, I'm showing two baselines, which sort of trade off the explore versus exploit trade-off in different ways. So on the left, we have upper confidence bound, where rather than exploring using our using our experiment context for exploration, it is actually exploiting those experimental contexts, i.e. it picks the treatment that achieves the higher reward in that specific experimental context, which means that we basically learn absolutely nothing about the true M star, right? Because the true M star is achieved at treatment 1. Our approach, we sort of select the all of the 3 experimental contexts are selected to be performed at treatment 1, which will be maximally informative about M star because we are learning precisely the realization of this curve. And complete exploration, we have something like an A/B test. So basically picking one treatment or the other uniformly at random. So basically no prior knowledge is used in this case. So the TLDR of this paper basically is we are aiming to perform a better contextual A/B test by formulating and optimizing a contextual max value expected information gain, which we call CMV-EIG. And this is the formula. Again, I don't think it's particularly insightful, but it is again a form of mutual information between our outcomes and the unknown quantities. This specific example, or all of the examples that we consider in this paper, constitute a form of implicit likelihood based on experimental design problem. So we don't have any of these likelihoods in closed form, and therefore we resort to black box mutual information estimators such as the InfoNCE that I briefly introduced a couple of slides ago. We also show how we can deal with discrete designs, which is something that I didn't really talk about during the presentation. But essentially, what we're aiming to do is optimize everything with gradients. And obviously, if we have any discrete variables, that might constitute a problem. And Gumbo softmax relaxations is a way of dealing with discrete variables in a continuous manner. I should update my slide. That was ICML last year. Right. So I have another a slightly extended version of the illustrative experiment where we have 4 treatments, and our contexts are on our experimental contexts are on this side, our test contexts are on this side, and different different baselines, right? So we learn to do an A/B test, right? In this case, the optimal thing to perform actually is an A/B test on action 1 and 2 only, which is basically what an algorithm like Thompson sampling will also perform. UCB will always pick the first action simply because it has a slightly higher standard deviation, and then random would also sample the very suboptimal the very suboptimal treatments, which will bring no information about the thing that we're trying to learn. Oh, that's just another experiment that I can skip over. In another line of work, we looked at Bayesian experimental design for active causal discovery, where the goal is essentially to find the most informative interventions that will help us identify an underlying structural causal model in the cheapest and most efficient way. There's some standard for causality assumptions that we sort of also assume. And I'm conscious of time, so I'll try to wrap it up in the next couple of minutes. So the TLDR of this paper that we call CPET, differentiable causal Bayesian experimental design, is very similarly to before, formulate an EIG and optimize it using gradients. We can think about it. We can think about this problem setup as trying to perform parameter learning plus structural learning, or essentially Bayesian model selection, right? If you are from that field. And finally, we have something that looks more into active learning. This is a colleague of mine's work on prediction-oriented Bayesian active learning, where rather than learning about parameters, we are actually looking at information gain in the predictions. So when you're in an active learning context, what you really, really care about is for your model to be good at predicting. And standard active learning so far has also focused on reducing uncertainty in the underlying model uniformly, which is not the task at hand. The task at hand is be very good at prediction. And this is what this alternative EIG, that we call expected predictive information gain, is actually seeking to do. All right. And limitations and future directions, I just want to mention one thing that is very much the focus of my Bayesian experimental design related research, which is model misspecification, where we can observe some really catastrophic failures. And here is a very quick example. Think about a linear model. The optimal designs for a linear model are always in the endpoints. Let's say if our design is constrained to be between -1 and 1, the optimal thing to do is to sample -1 and 1 equally often. And if the underlying model is not linear, you will not be even able to detect the model misspecification if you were relying only on the data that is the output of your optimal experimental design setup, right? In panel B, I'm showing random design, right? And I'm still showing a linear fit, which is much closer to the true data generating process compared to the one that we estimate from the optimal design. So model misspecification obviously is a very big one. I'm not claiming that we can solve model misspecification overall. It's a very hard topic. But sort of the questions that I'm thinking about is, can we formulate more robust objectives? There are some works of other groups that have made some progress in towards this goal. And, you know, a follow-up would be, can we try to fix the model somehow? A few other things that are kind of fruitful areas for thinking about future research. I think number one is getting better at software and engineering. I'm very excited about an open source project called Baseflow, which is a library for simulation-based inference and amortized inference. And I'm hoping to bring in some of the Bayesian experimental design capabilities into that as well. Things like reinforcement learning and active inference. So the policy-based Bayesian experimental design that I described in this presentation is getting very close to, the field, much closer actually to the field of reinforcement learning. And I think, there can be some interesting things that we can borrow from the field or that we can hopefully teach the field. And finally, real world applications, and thinking about real world applications is always important. If anyone is working on any sort of concrete problems, I would be very happy to chat to you, as our group is sort of actively looking for, real applications to sort of think about and help with. So with that, I would like to thank all of my co-authors and collaborators and see if there are any questions from the audience. Thank you so much.